Hi, and welcome to Lecture 3, Module 1. Lecture 3 takes us from the world of bivariate hypothesis tests and bivariate regressions to the land of multiple regressions. The major difference is rather than having only one single independent variable, we're going to have many independent variables. Okay. Now, we're not going to get into the whole possible range of multiple regression topics in this course. Instead, we're going to go through in this lecture some of the fundamentals of multiple regression, and in the next lecture, we're going to discuss some variants and some options. Okay, so first let's review experiments. So the point of experiments was that we have random assignment into treatment and control groups. Right? Both groups have similar characteristics. They differ primarily in the fact that one has the treatment applied to it and one does not. We said at length, though, in an earlier lecture, that the typical political science study, or any social science study, does not have random assignment. Right? If we want to know if religion influences approval of the president, people aren't randomly assigned to religion. So in general, we can't get random assignment. It may not be ethical if we can, and usually we can't. So random assignment is difficult, and we're going to fall short of the sort of gold standard of the randomized controlled trial, even though there are increasing numbers of those experiments in political science. Okay, there are increasing numbers, of course, because random assignment does cure many problems, right? When the groups are the same and they differ only by the treatment, then they gain internal validity, and we can increasingly assign differences in the groups as due to the treatment and not due to something else that would otherwise be possible, but is not necessarily because of the similarities in groups besides the treatment. Now, we're focusing here on observational data in which we don't have random assignment. Because of that, we must statistically control for potential confounding variables. So we're going to do that with multiple regression. Now, why use multiple regression? Well, we might have multiple hypotheses, and we're trying to infer that each of our independent variables in our hypotheses causes some dependent variable. Or we might have one primary independent variable of interest in one hypothesis, but think there are many confounders, many things that might alter our ability to make assessments of causality. The regression models themselves only show correlation. We must infer causation as usual. And to infer causation, as usual again, we must rule out alternative explanations by rejecting the null hypotheses for these. Going back to a while ago now, spuriousness was an important confounder we discussed, in which there might be another factor, z, that we're not considering, and if z leads to x and z leads to y, then it might not be the case that the correlation between x and y is due to any causal relationship. It might instead just be due to z causing x and z causing y, and therefore we think x and y seem to correlate, but really the correlation is spurious. It's not real. It's not really due to some underlying causal relationship between x and y. It's due to z causing both. So the multiple regression model is a nice way to control for spuriousness, to control for this additional factor z that might be affecting both x and y. And even when x and y are connected, but it's not as strongly as you might think, spuriousness can still play a part. In other words, spuriousness doesn't just arise when z causes x completely and z causes y completely, and there's no relationship between x and y. Spuriousness also occurs when x and y are related for real, causally, but z also causes x and z also causes y, so you have multiple interacting causes. Okay, so what is the multiple regression model? Well, it's this top equation here in the slide. It looks very similar to the original OLS model for bivariate, in a bivariate regression. The difference is this last term. We still have a dependent variable y on the left-hand side. We have a constant alpha on the right-hand side. We have our first independent variable x, and it's multiplied by a coefficient beta. The only difference here is we now subscript beta with a 1 to let us know it's the first coefficient corresponding to the first independent variable. Now we add a second independent variable, z, And this z is the variable that we think could possibly be leading to spuriousness in our regression, in our model. And before the z, we have another coefficient, beta, with a subscript of 2, to let us know this is the coefficient on the second independent variable. Okay. So again, y is the dependent variable, x is the independent variable, and z controls for spuriousness. By including z in the model, we can examine the effect of x while holding z constant. That last phrase is absolutely key, and that underlies all the stuff we do. And in fact, in the next module, we're going to go through some calculus to see how it actually holds z constant, just because it's so important to understand that deeply. The reason we include z here is because by including z in the model, we can examine the effect of x on y while holding z constant. Because of that, we can see how x influences y without worrying about z's effect, because z is constant. Z is held constant in that effect, and therefore we can ignore the spuriousness of z. That's really important. Right? Now we have z and an x. They're both independent variables. The difference is we tend to call the one we care about most, the x, the independent variable, and the z, which is just there to control for spuriousness, the control. But technically speaking, they're both independent variables, and if we flipped our interest to z with x being the control, it wouldn't change anything in the model. In terms of the logic, it's very similar logic to standard OLS in a bivariate regression. The difference is, instead of fitting a line to minimize the error around the line, minimize the sum of squared error around that line, we fit a plane to minimize the error around the plane. So plane here is just a two-dimensional surface in some higher dimensional space, three-dimensional space here, and we fit that plane to minimize the distance, the square distance between the plane and the data points, the sum of the square distance. Okay. So again, it's a fairly straightforward extension by just adding more variables. So a bivariate regression has y equals alpha plus beta x. A multiple regression has y equals alpha plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, and so on until you finish off with the last independent variable x sub k, which is multiplied by a coefficient beta sub k. The key is this fourth bullet point. It's absolutely key. Each beta in this regression tells us the partial effect of each different independent variable while holding all the others constant. I'll say that again because it's so important. Each of the betas here tells us the partial effect of each different independent variable holding all the other ones simultaneously constant. And we can further figure out if we have statistical significance for each one of those coefficients. We can tell with 95% confidence if each one is different from 0 by treating each one separately and doing a separate t-test for every single coefficient independently. So all the stuff we did before with bivariate regression all still holds. We can analyze things the same way. The t-tests are the same. The standard for statistical significance is the same. The method to obtain it is the same. And it all comes from the fact that this multiple regression treats the effect of each independent variable on the dependent variable separately as if it's holding all the other variables constant. Now, that does not solve all problems with spuriousness. This only deals with things that you can actually measure. You have to measure them correctly. You have to put them in the model correctly. If they're more complicated models than this linear thing, then you have problems. If you don't measure it correctly, you have problems. There's tons of ways to... Or if you have a variable that would have induced spuriousness that you failed to measure, that's a problem. That's called omitted variable bias. But all that said, this multiple regression framework gets us a lot further than the bivariate regression framework did, and we're going to use it extensively in social sciences, and we'll do a bunch of examples now in this module, in the next few modules. Okay. So let's compare them. In the bivariate, we have y equals alpha plus beta x. in a multiple regression with one control variable, we have y equals alpha plus beta 1 x1 plus beta 2 x2. The key that relates to what we just talked about in terms of the way of interpreting the beta 1s and beta 2s is that these things mean different things than the original beta. Beta 1 in the second regression is not the same as beta in the first regression, even though they both multiply in x. That's also key. It depends on the degree to which x2 actually influences x1 and y. If x1 and x2 are unrelated, then beta 1 will be pretty close to beta. We'll look at that again later in this module. If x2 does affect x1 though, and also y, then x2 would have induced spuriousness, and we'll find that beta 1 will be much different than beta. Because beta 1 is a coefficient telling us the effect of x1 and y holding x2 constant, whereas beta is the effect of x on y not holding x2 constant. So we have very different models, and the betas they produce are going to be different. They mean different things substantively, and when you actually do the regressions, you'll get different numbers out that have different values, so they mean different things empirically as well. So it's really important not to confuse the beta with the beta 1. They're different coefficients, they're different estimates, they mean different substantive things. Okay. So how does this all work? How does the model control for z? Well, z, we're assuming, is related to both x and y. Z explains some of the variation in x, and z explains some of the variation in y. The formula for beta 1 will not use all the variation in x and y. It will use the variation in x and y that cannot be explained by z. So you take out all the explanation for the variation in x and y that z can explain. What's left over will be in the formula for beta 1. So to repeat, and I'm repeating this a lot because it's important, if y equals alpha plus beta 1 times x plus beta 2 times z, then beta 1 is the effect of x on y controlling for z, and beta 2 is the effect of z on y controlling for x. If you have more than two independent variables, each of the beta is the effect of that particular independent variable holding all the other independent variables that you included constant. It doesn't hold independent variables constant that you didn't include explicitly. If you missed a variable, you still have the same problems you had before. But if you measure and include the variable in your regression, in your multiple regression, then the estimate for your earlier betas will be holding the other variables you included constant. Okay, so let's do an actual concrete example. And the question is, what caused someone to vote for President Obama? And the three typical, three of the most common explanations for any kind of vote choice are the vote you make will equal a function of, there's a constant, your income, beta 1, partisanship, times beta 2, and ideology times beta 3. But what if our primary interest is in income, the effect of income on vote, and that's what we're going for first. So let's treat income here as the primary independent variable, just conceptually. All these are independent variables, but let's conceptually look at income as the one we're thinking about most to start off with. Okay. And that's sort of the research question. We want to understand the effect of income on the vote. The thing is, ideology and partisanship will not only affect the vote on their own, but they are also related to income. So we wanted to control for them because otherwise we might get spuriousness. Because partisanship and ideology correlate with income and with vote. Beta 1 here, though, will tell you the effect of income on the vote, all else equal. That is, they'll tell you the effect of income on vote in which only income varies and we hold ideology and partisanship constant. What that does substantively is it allows us to compare two people with identical ideology and partisanship who differ only in income. So, a dependent variable here is going to be voting for Obama, 1 to vote for Obama, and 0 to vote for McCain. This is technically dichotomous. There are categories. So technically, we really shouldn't do it the way we're going to do it, but we'll get to that in the next lecture. Let's just do normal OLS for now. Our primary independent variable will be 0 to 4, corresponding to increasing income categories. So this is an ordinal variable. And then we're still going to use OLS for this. Okay, so our model will start off with a simple bivariate model. And we have y equals alpha plus beta x. We have income and the constant, and this is the same kind of table you've been seeing recently, right? There's a column for the estimate for the coefficient. There's a column for the standard error of the coefficient. And there's a t-ratio, which is just the estimate divided by the standard error. And it's a t-test. It's your statistic for your t-test. And again, sometimes you might have a fourth category for the p-value, I guess fifth category in this case. For the p-value, we don't have it here, but that's okay. So our predicted values, again, y equals alpha plus beta x. If you plug in these estimates, we can predict y hats for this. And if you're in the lowest income category, you would take the lowest income category, which is 0, multiply it by the income, so you get 0, add the constant, and that means if you're in the lowest income category, you have a 76.7% chance of voting for Obama. That's your predicted chance. If you're in the highest income category, you take a 4, you multiply it by income, you get negative 0.32, you add that to the constant to get 44.7% chance of voting for President Obama. That's a very, very big difference. That's a 32% points difference, and significant. You see that the t-ratio here is negative 8. 8 is bigger than 2, so we're going to say this is a statistically significant effect of income on vote choice, and substantively, it's very, very, very big. So this seems great, right? If we were doing this analysis, well, okay, it's not great substantively, or normatively, but from the point of like answering our research question, we've produced an answer that seems very strong on its face, right? We've said, yes, income does have an effect on vote. It's a statistically significant effect, and it's substantively very large. It's 32%. But we've missed a lot of possible variables that could have affected the outcome by acting through both income and through vote and on the vote directly, and that might mean we have spuriousness that renders our estimates biased. Our estimates of the effective income biased. So what we're going to do is we're going to do the same variables as before, but we're going to add 2 more variables. One for partisanship, which is going to be negative 1, 0, 1. So it's effectively an ordinal variable in this context, even though there's a natural order here. We're saying more Democratic means you are more likely to vote for the Democratic candidate. So here it's like an ordinal variable. And also an ordinal variable for ideology, which runs from 1 to 7. Very conservative, very liberal. And we've chosen all these directions so that positive values and everything in partisanship and ideology should lead you more often to vote for President Obama. Okay, so what do we get now? We do the same, we do a multiple regression, and the software gives us these answers, right? It calculates the different values of the coefficients, and it tells us estimates again, and errors and t-ratios. What happens? Well, now we have, first of all, partisanship has a 0.34 estimate for its coefficient, with a very high t-ratio, so it's clearly significant, and pretty large it seems. Ideology is somewhat similar. It seems smaller, but keep in mind ideology goes from 1 to 7. So a 4-point spread there would be 0.28, which is a similar order of magnitude of partisanship. And this, too, is well above the bar for significance. Our income variable, though, now, the estimate has dropped. If you recall, it was negative 0.08 before. Now it's negative 0.016. That's a factor of 5 less, right? That's a factor of 5 less. The t-ratio now has also dropped. It's still barely significant, but it's really close. So now the effective income overall seems to have decreased. We can check that by, again, predicting our values on vote. So if a person's in the lowest income category, again, this is 0 for income, we get in this new model a 63.54% chance of voting for President Obama, holding all other variables at their means. What does that imply, to hold other variables at the means? Well, keep in mind now, your regression equation looks like this. Over here, if I want to predict vote, I need to insert the constant, the income times its coefficient, but also the partisanship times its coefficient, and the ideology times its coefficient. When I do that, I need to pick, if I'm just trying to understand how the lowest income category works, I need to pick values for partisanship and ideology. So the norm here, and there's no one answer, but the norm is to use the means or the medians or the modes for the values of those other variables and calculate the effect of different income categories holding the other variables at their means. In this case, the mean for partisanship was 0, and the mean for ideology was 4. So you'd plug those in, and what you get is this. Now, if I take the same values for partisanship and ideology, but now go to the highest income category, I get 57%. That difference is only about 6.5 percentage points. You can also see that just by multiplying 4 times the income coefficient. That would be the difference between the lowest and the highest incomes. And again, that's about 6.5 percentage points. That's much different than from 32. Right? Before we had an estimate of 32 percentage points difference in the bivariate regression. Now we have 6.5 percentage points. What happened? What changed there? Well, what changed is that income was related to both partisanship and ideology. In the very first model, the coefficient for income was capturing not just the effect of income on vote, but also some of the effect of partisanship and ideology on vote. So it's artificially inflated to seem much more important than it was. We call that omitted variable bias, I think in bold right here. It's when you omit a variable that was important, because without it you would have had spurious causation, and because of that omitted variable bias, you get a biased estimate. It is not accurate, right? Because the estimate of your beta 1, or your original beta 1, was incorrect because it included the effect of the z variables, the control variables of partisanship and ideology, as well as the independent variable. In this case, it overestimated the effect of the independent variable on the dependent variable. Okay. So that's how this all works, and that's why we include these controls. I'll close with another way of looking at it that's a little more graphical, that might also be maybe clearer potentially, or maybe less clear, we'll see. So here, there's a y, a dependent variable, and an x and a z. And this is a Venn diagram, you may remember from many years ago. We're assuming here in this Venn diagram that y is related to x and z, and that x and z are also related. If we exclude z from the model, if we don't include a model, we're looking at y and x, then what happens is the effect of x and y is related to d plus b over here. Problem is that's a mistake, because d is the portion of the variance of y that's shared by both x and z. So when we look only at how x affects y, we're including all of this when only part of it should be included. Right? Only part of this d here is actually due to x by itself, the rest of it's due to z. But if we ignore z, we're including all in x's effect, and the effect of x ends up seeming different than it actually is, different from the way it should be. Now, this problem does not exist if x and z aren't related at all. If x and z have no relationship, right? There's no common variance. They don't covary. Then if we exclude z from the model like this, the effect of x on y is b, and if we include z from the model, the effect of x and y is still b. Nothing changes. So if x and z aren't correlated, that doesn't matter if we include z or not. The thing is, in practical use, it is almost never the case that we have absolutely no correlation between a variable and between x and z in this case, between the variable of interest and other important possible controls. So if you go on in trying to assess causal inference, one of the things people do is draw very carefully diagrams of the causal pathways that link all the variables in your model, so you can try to control for things like this. Okay, so that's where we're stopping here. In the next two modules, we're going to take a step back and talk about some mathematical foundations that are necessary for understanding what we just talked about in a little more depth, and then also will be helpful going forward in whatever career you choose. Thank you very much.